most of your particle physics, right? So assume that you have some BSM model, for example, say SUSI or something, and from your theoretical predictions you have some prior, right? So that one can use that kind of thing as prior probably, and then given that you observe some data and you see how compatible is your data given uh, that particular theory, that's the likelihood. Okay, the likelihood is that if this theory is true, then what will be the observation of the data? Okay, so that gives you the likelihood, and given that likelihood, you re-estimate, you get the posterior probability. So assume that you expect some, some resonance at mass, some parameter value at some values, but the data actually doesn't prefer that value and prefers some other value, even if that that parameter actually exists, and so the data will not be exactly matching to what you exactly expect from that theory. So the likelihood construct the compatibility between these two, and given that likelihood you will get the posterior probability. That's what I understand.
Then there's this question: is there any guidance to choosing the prior?
mm, there is, as I said, there is no I mean preference ways of choosing the prior. I mean the theorem doesn't say anything, but maybe the people who do Bayesian statistics, they have some preference.
I just know of one thing. Once, I mean, I was hearing from this Harrison Prosper, who is a very well-known statistician in high energy physics. So what he said, so not Harrison Prosper, sorry, Louis Leon, and what he was saying that you just ask your theory friends, they will tell you what prior would be good in your theory, because they would know how much belief they have in their theory. So that is one way.
Okay. Okay. Anything else? References, I think I have in my slide, in the very first slide. So there are the reference, the books, 2 3 books that were listed. Okay, if there are nothing else, probably we can probably start, right? We have 10 minutes pass. Okay, so let me restart from this central limit theorem, which where we ended last yesterday. So what we discussed in this is that if you have several say random independent random variables with n very large, okay, and you simply do a sum or average of those random variables, the value that you get some is again some variable, and the distribution of that variable would be basically a Gaussian distribution with mean is sum of the means, and if you take average, that will be the sum of average of the means, and the um, uh, variance would be again sum of the variances. If you take the sum, or if you take the average, it will be the average of the variances. That's what it tells, and it is almost independent of the PDF of the exercise. Okay, now let me go to um, another uh, distributions. So I did not finish all these distributions yesterday. So there are, although I will not cover almost everything, but few important ones I want to cover. So here another one which is largely used in high energy physics experiments. It's a log normal distribution. So the log normal is that if you have say variable y, which is a Gaussian, with a mean mu and variance sigma square, and you do a transformation of that variable as x equal to t power y, and then the x would follow the log normal distribution. So you can simply see that here in this case, here x is replacing log of x, and then there is a term 1 over x here. Um, so this has an equivalent of central limit theorem. So in central limit theorem, we said that if you take sum over xi's and then the sum will follow a Gaussian distribution. In this case, if you have random variables xi's and you take the product of all these random variables, then the product that you will get will follow a log normal distribution. So therefore, usually when we have random errors from random sources that change the result by a multiplicative factor, so these uncertainties are usually modeled as a log normal distribution.
Arun, can I just confirm one thing? So when you have written y is equal to product of all xi's, xi follows log normal, meaning if I plug in xi individual follows log normal, right?
No, that's
It's
not.
log of, sorry, so log of x will follow Gaussian, right? That's what it means. Or, oh no, sorry, you are saying
And
in
I'm
general,
saying that
in
in
general.
general, in
Okay, in
general.
general. Okay,
Yeah.
okay, okay.
So because see, if you take it's like a log of this sum it's a sum of this, right? Log x. It's a log of this product is a sum of log xi. So that makes y it's like a sum of all this log of xi. Log of
Yes.
y is sum of log of xi, like that. Yeah. Okay. And so you can see the distribution here. So the distribution is only positive. So you can see that it's not symmetric. So it has a long tail. So in this case, here for this distribution, the mu is 0 and the sigma is 1. And just remember that this mu and sigma are simply the parameters of this log normal distribution, and they are not the mean and the standard deviation for this distribution. Instead, you can show that the mean of the distribution is exponential of mu plus sigma square by 2, and the variances will be exponential of 2 mu plus sigma square times exponential of sigma square minus 1. So you can actually do this exercise yourself. Okay, and then the other distribution, which is very important for not only HEP but for all data analysis, is the chi-square distribution for any continuous random variable. So if for a variable z, and for this case the z is always greater than or equal to 0, so the chi-square distribution is defined like this: 1 over 2 to the power n by 2 and gamma function times z to the power n by 2 minus 1 and the exponential function. So in this case, this n, which is the parameter of this function, is it corresponds to the number of degrees of freedom, and if you calculate the mean and the variance of this function of z, then the mean would be equal to the number of degrees of freedom, and so this would be capital V, and the variance is twice the number of degrees of freedom. Now, where do you get this kind of variables? If you take, say, n independent Gaussian variables, xi's with mean mu I and variance as sigma I square, where xi's are Gaussian distributed, and you take simply the summation which you define when you get this in least square fit, if you have done already, or will come later, maybe tomorrow or day after tomorrow, about this, discuss about this, that when you define a least square um, between the variable and the mean, okay, so this is the sum of these differences, square of the differences. So this function z follows the chi-square distribution with n degrees of freedom. So that's why we usually call this as chi-square. This we call as chi-square fit, or usually the least square fit is also called chi-square fit.
And there is a question for chi-square distribution. Is it necessary for z to be a continuous random variable?
Uh, z is a continuous random variable, by definition. And so here the z is coming from this, where x is a continuous random variable. Okay. Uh, so these kind of things that you not only encounter in simple chi-square fit, but you also do the mean square error in ML, where you try to minimize the mean square error. So mean square definition of the mean square error is same as the least square here, and in that case you also should expect that the variable that you are minimizing is the minimum of that should be according to the chi-square distribution. And so this, I think, plays an important role in goodness of fit test, which we'll discuss later in the method of least square. Okay, and the other distributions which are also useful for modeling many different things. One is the gamma distribution, where for um, x greater than equal to 0, then you can define the gamma distribution, which is f of x alpha beta, which is defined like this. I think yesterday Shilpi showed this one, that if you simply add two exponential, it will become a gamma distribution. And in that case, the definition that she gave is where the beta is actually 1 over theta. So see, I mean, in terms of 1 over theta. And so in this case, alpha and beta has to be greater than 0. There should be positive parameter, and alpha is called the shape parameter and beta is called the scale parameter. So you can see for beta equal to 1, if you change the value of the alpha, how you see the distributions. And you can show also that the mean would be alpha by beta. And so if you take beta to be 1 by theta, it should be alpha times theta, and the variance will be alpha beta square. Okay. Then similarly, the another distribution is the beta
There
distribution.
is a question, where do we
Yeah.
use gamma distribution?
Yes, I think this is use one thing, probably also the energy loss in the detector. One can probably model this. And second thing, as much I remember, probably it's the gamma, the distribution of uh, in the gamma sources, the angular distribution of particles from gamma sources is probably modeled like this. I am not sure. Anyone else knows?
Yes, I also know that the energy loss is what you said
Yeah.
exactly about the energy loss.
And then you have also the beta distribution. The beta distribution here has similarly again for positive x. And so here you have this the definition, as you can see, the x to the alpha minus 1 and the 1 minus x to the beta minus 1 over a beta function, which is kind of function of alpha and beta. And you can see the distribution here. It has an interesting distribution. You can see that this distribution is symmetric in alpha and beta. So when you take, say, alpha and beta to be same, then this is symmetric in x between 0 and 1. Okay. And when you increase alpha and decrease beta, then it tends to become maximum towards the positive side, towards 1. And when you decrease alpha and increase beta, it becomes mm, um, uh, maximum towards the 0. Okay. And you can calculate the mean, I think, only uh, when alpha and beta are greater than 1. For below that, there is some difficulties in this case. Okay. The last one is the Bright-Wigner distribution. So in this case, this is also called the Lorentz distribution or Cauchy distribution, and this is used to model the resonance mass or the distribution of the resonance. Right. So here you have the mass term in this case, and gamma represents the width of the distribution. So then you can see that if you have, say, for Z boson peak or other di- distribution of or the particle mass, so you would model this with this Bragg-Wigner distribution. And the gamma here is basically not exactly the standard deviation, but it gives the two of twice gamma is equal to the full width at half maximum. And in this case, it is important to note that the mean and the variances are undefined, because if you calculate integration of x of f of x fx dx and x square f of x dx, both would be divergent. Okay, so uh, if, then I can move to the next part, which is the multi variable distribution.
So there is a question, do we always know which PDF to use?
It depends on what you want to do. As I said, this if you want to model, say, the mass distribution, you would prefer to do this Bragg-Wigner distribution. But if you want to use, say, energy loss, you would use probably gamma distribution, or there is also Landau distribution if it's a thin detector. So there are, you know, mm, depends on the problem, of course. So where do you want to use? And if you want to model uncertainties, you either use Gaussian distribution or log normal distribution, like that.
Then there's another question, is the distribution with a mean and variance which is divergent useful?
Yes, this is what we are using in this case. It is divergent in the sense that you cannot calculate analytically, but in reality, though, since you have finite number of events, you can always calculate that. So, but it's not defined in that you cannot actually calculate analytically, but
And
numerically you can still do it with finite number of points.
and also sometimes one can define 68% of the interval
Yeah,
or
yeah.
just take the peak, but these are useful.
Yes,
And
yes.
yeah.
Also, in case of Landau, probably also there is a the sigma is not defined, if I understood correctly. But that's we use for the energy loss distribution. Okay. Mm, let's see. Let's go to the next one. So the joint PDF. So suppose we have more than one random variable. Say in this case, I'm taking just the two. Then you can see, for example, this plot here, which is in x it is an exponential distribution, and in y it is a Gaussian distribution. Okay, in this case, the joint PDF f of xy is, suppose you take, say, um, in this plot you take some region where this region is y and y plus dy, and this region is x and x plus dx, between x and x plus dx, and then the overlap region, or you know probability of events falling within this a and b, that is this region, would be can be written as f of xy dxy, where f of xy is the joint PDF of this distribution. Okay, and the normalization condition requires that the integration over f of xy dx dy, it should be 1. Okay, now from this joint PDF you can always calculate the marginal PDF. Marginal PDF is the PDF of x irrespective of y. That means you can simply say project the to the x-axis. Okay, and so that which you can write as, if you simply integrate over the y, that the PDF that you will get will be one dimensional PDF. So that is called the marginal PDF in x. And Here you can see the marginal PDFs, which are projections into individual axis. So in this case, if you project to the x-axis, you get an exponential distribution. If you project to the y-axis, it will be a Gaussian distribution. But since in this case, this variable is correlated, so the y depends on x. That's why in y you have a mean which varies with x, and that's why you do not get exactly when you project it, but you have a slightly bigger tail on the right. Okay, now let's define conditional PDF. So conditional PDF is, suppose you have um, uh, say y, the probability for y to be in y and y plus dy, and x, given that x is in x plus dx, it's that is you treat x to be fixed. Say, let me take like this. Suppose I say that if I have I keep the x equal to 5, then what is the PDF of y? So that's the conditional PDF here. Okay. So that means, as we have from the definition of conditional probability that we defined earlier, that probability of B given A, which you can write as probability of A and B over probability of A, which is basically the whole probability in the region dx dy over the probability of A at x. Okay. So that we can write in terms of the variable itself, that the h of y given x is the full probability f of xy over the f of x. Similarly, you can also write the probability of x given y. So that's the whole probability, joint probability over the marginal PDF of the y. So if you replace these things here, then the base theorem in terms of the variable itself will be probability of x given y would be the probability of y given x times the marginal PDF of x over the marginal PDF of y.
There's a question again. In the previous slide, what did the error bar signify in fx and fy?
Here. So this is just a statistical error. This is since I just projected to the individual ones, so this would be simply the square root of that number. Yeah. Okay. Um,
Then how do we project?
how do you project? Yeah, that's what I said. So if you want to project this, you basically integrate over the y, right? So projection to x-axis is basically you have the whole PDF here, and you integrate for all y. Okay, then you can um, um, project to this x. Okay, so whatever distribution is in only in x, that you will get. Okay, you can technically you can do it in Python or root. If you have seen the histograms, 2D histograms, there is a function called project x and project y. You can use that. So that's basically for any value of y, what is the distribution in x. That's all. Okay. Now, if A and B are independent, um, then you can write that probability of A and B is simply the product of the probability, their individual probabilities, P of A times P of B. So then you can also write the same thing in terms of the variables itself. That means if X and Y are independent, then uh, the joint probability is simply the product of their individual probabilities. Okay, that is the corresponding PDF can be factorized. So here you can see how you can write conditional PDFs. So as I said, the h of x here is h of y given x is the probability of x y over the probability of x, okay, at point x. So that you can do. So for example, if I take choose my x equal to x1, then so this is x1 plus x1 plus dx kind of things. I just take this small region. So then you can see what is the distribution in y. So this is Gaussian, but with a mean value say around 5, okay. And then when you go to a different x values, as y depends on x, so if I choose a different x value here, x2, then it would again be a Gaussian distribution, but with a different meaning of the y. Okay, so that is what you get. So these are um, that's how they depend on each other. Okay. Mm, now let me go to now if we have say a joint PDF with say at least two variables, then you can find the covariance of these two variables, where the covariance is defined like the expectation value of x minus expectation of x times um, y minus expectation of y. Okay, for variance you wrote basically the square of the expectation of the square of x minus x x mean. Now in this case you have both, so that you can rewrite in terms of I know factorize it and do simple algebra, and then you get this is simply the expectation of xy minus their individual product of their individual expectation values. So that you can write then in terms of PDF like this. Okay, so given this covariance values, then you can also define the correlation coefficient. So the correlation coefficient is simply the covariance of xy over their individual variances or individual standard deviations. And the correlation which usually coefficient is usually varies between -1 to 1. Okay. And if your two variables are independent, that means if you can factorize their PDFs to their individual PDFs, then in that case this term here uh, would be can be simply factorized. So you can write this as individual um, integrations, okay, and then that will be basically make it same as the product of their means, and so the covariance will be 0. Okay, that means if they are independent, they will be the covariance will be 0, and if the covariance is 0, x and y are uncorrelated. But in some cases you might get the covariance still 0 because there are some positive and negative term cancels out. I mean, by some cases these two become same even if they are not independent. Okay, in that case you will get covariance 0, but that doesn't always mean that x and y are independent. So if they are independent, the covariance becomes 0, but if the covariance becomes 0, doesn't always mean that they are independent, but they are uncorrelated. Okay. Um, say let's see let's see a distribution um, uh, for more than one variable. So in this case, the first one is I'm discussing the multinomial distribution. So in this is basically a generalization of the binomial distribution to the case where you have m different possible outcomes instead of just a binary outcome, success and failure. You can have multiple outcomes, like say you are throwing a dice, two dice together kind of things. So you have multiple possible outcomes. So suppose you have the probability of each outcome is I for a particular trial, and that the probability for this outcome I for the particular trial is the pi, and then you can write that sum of this pi's has to be 1. Okay, because it's conservation of probabilities. Then you can write the joint probability to observe say n1 outcomes of type 1 and 2 outcomes of type 2 and so on in total n trials, which if you just generalize the binomial distribution to this, it will be basically this binomial coefficient times the product of their probabilities for n1 uh, um, outcomes of type 1 and 2 outcomes of type 2 and so on like this. So from here, you can also, earlier we saw that for the binomial case, the mean is pi, right? So in this case, you can also show that the mean of ni would be n times pi, and the variance would be again n times pi times 1 minus pi. Okay, and now, if you rewrite this, take a special case of this multinomial distribution to just three possible outcomes like outcome I, J, and everything else. So then you can rewrite this in terms of just I and J. So where you will have say n factorial over ni factorial nj factorial times this n minus ni times nj factorial. So everything else would come like this except these two. So this is basically generalizing the binomial to just three possible outcomes, and here also you'll get exactly the same kind of things. You can calculate the covariance for ni and j, which is generic not only for this but also for the multinomial distribution. So you can calculate the covariances for ij, and that covariance for ij should be minus n times pi pj, that you can show. And if um, I and j are same, that means the variances for individual ones, that should be same as what we got previously. Now, if you go to the multivariate Gaussian distribution, which is again a generalization of the Gaussian distribution to n-dimensional vector x. Okay, so here in this case, if you know the covariance matrix V, then you can write, I mean, this is written in terms of this covariance matrix V. So here, instead of the sigma, you have the inverse of the covariance matrix times this vector, okay, the vectors. So in this case, x and mu will be the column vector, and then the expectation values and covariances can be found for for the mean. They will be say similar to the Gaussian one. Okay, individual means would be equal to mu I, and individual variances would be equal to sigma I square, while you have additional covariance term. Okay, so if you simply write this for two variables x1, x2 or xy, with mu1, mu2 as their mean and sigma1, sigma2 as their standard deviation, and um, write in terms of rho, which is the covariance over their individual standard deviations. So then you can rewrite this function in terms of like this. Okay, so this is the 2D Gaussian distribution that you can say, where rho is the correlation coefficient that we defined earlier. And this distribution now you can see in these plots. So if you take say, so these are all with a sigma 1, sigma 2 equal to 1, okay, and with a different correlation coefficients. So if you see, if you say take coil rho equal to 0.7, then you see the distribution like this. Then you take rho equal to minus 0.7, which is anti-correlated, then you can see the distribution changes. And this one is for the very highly correlated, close to 1. So here in this case, rho equal to 0.95, and this is less correlated, so equal to rho is 0.2. Okay, so if when you have rho to be 0, then you should see just kind of a circular distribution. Okay, now coming to the next one. So the next one is the functions of a random variable. So if we have, say, imagine that you have a random variable x with some PDF f of x, and then you want to have a function a, which is a function of x, and this is a continuous function. Then the problem here is, how do we find the probability distribution of a? Okay, because many times we do a transformation of our variables, and we need to know what is the PDF of that after we do the transformation. So in this case, say, here you can see when x varies by amount dx, you can see that the a varies by amount dA. So then you can write, if GA is the probability distribution, PDF of a, then you can write that GA times dA would be simply integration over this region ds of f of x dx. Okay, then from here you can convert back a in terms of x, that if a can be inverted, then you can write from this conservation of probabilities, then you can write g of a is simply f of x a over dx by dA. And using this you can do variable transformations from one variable to some another variable. Okay, so in some cases you may have situation where the A doesn't have a unique inverse. So in this case you might have to actually include all possible intervals. So as this in this example, so in this case you have two possibilities for when a changes by dA, dx changes in x changes in different places. So you have an exercise here to calculate what is the PDF in this case if a of x is given like a square term, x square. Okay, okay, now if there are more than one random variable, say n random variables x1 to x2, and a is a function of all these random variables, okay, then in this case uh, you can do exactly similar. Okay, so let's say here um, you have the x and y are two random variables in two dimension, and the a is, say, or z is x times y. Okay, so which you can imagine in the z axis. Now when um, z changes by z plus dz, then you can imagine that the x times y would change by a factor like this. Okay, so in that case you can again write in a similar way, that you can write this g of a dA would be basically over this region, write f of x, f of xy dx dy kind of thing. Okay, now you can take an example here. Suppose you have two independent um, variables x and y with their PDFs gx and hy. Okay, now you take this xy, then find what is the PDF of z. Okay, so then you can actually if they are independent, then the PDF would be factorized, will factorize. Then in that case you can simply write f of z dz is g of x times h of y times dx dy. Okay, and then you can rewrite one of the variables in terms of z. Say this can be made it like this. So replace y in terms of z. Okay, so this should be actually dz. No, yeah, yeah, it's okay, it's correct. So then when you rewrite in terms of y in terms of z, then you write f of z would be, then the integration of y will go away, so you will have dz terms, and then at the end you will get f of z to be integration over the x region times g of x, and h of y is in terms of z by x times dx by x. Okay, and similarly if you can do other way, then replace x in terms of z, then that will give say g of z by y, h of y dy by y, and both should give the same result. And this kind of thing is called Mellin convolution. And you can have similar things. Instead of z equal to x y, you can also write it is a sum. So z is x plus y. So this is the example that yesterday Shilpi said, that if you have two variables, um, and you add the two variables, what is the PDF of the, the sum. Okay, so here you can also calculate in different ways using this case. So here again, if you write z equal to x plus y, then f of z will be, again you replace y in terms of x, would be, you will get this kind of thing, and or this kind of thing, both of them are equivalent or equal. So this kind of convolution is called Fourier convolution. So now you can do the exercise that I showed in the very beginning, uh, throwing up two dice simultaneously, where each of them were uniform, and you got a triangular distribution, if you remember correctly. um, so you can analytically find this result, that if you simply take two uniform random numbers, say 0 to 1, and then add each of x and y varies from 0 to 1, and add them to the PDF of z should be a triangular distribution in the region between 0 and 2. Okay, so this you can show starting from here. Okay, now when we have a function which is function of more than one random variable, you have this joint PDF. Sorry, I confused. So in this case, instead of, sorry, 1 minute. Okay. Yeah, sorry. I was here. Here I defined a is just a one variable which is a function of a vector of x. In this case, I'm talking about, say if you have x, which is a vector of, you know, variable xh, and then you have again a set of variables ah, which is, you can imagine that as a vector of ah. So then if we have a ah are functions of xi, then you can write the joint PDF of ah, which is g of a1 to an, is simply the PDF of f of xi times this determinant of this Jacobian. Okay, where the Jacobian is defined like this, which is basically the is a matrix with um, derivatives of del xi by del ai. There is a question if there is a way to tell if the variables are independent. Mm, Not fully, I think. You can calculate only the correlation coefficients, so rho, and you can still, it may not fully confirm that they are independent. So there is, for example, if you take say like this, as I said, uh, these kind of things, and then you make a dependency like this, that the a varies depending on the x, meaning of a varies depending on the x, and then make the PDF of the joint PDF of a and x, then you may not, you may still find um, the covariance to be 0 in some cases. And I think I had an example, I somehow missed that. I do not remember where did I put that. So some distribution, so where you can still have covariance 0, because something that may cancel out, and you may not get the, I mean they are still probably not independent. But in most cases we actually try to find the correlation coefficient or the covariance. If the covariance is 0, we think that there is the correlation is 0. That's the easiest way. I do not know if Shilpi knows something else.
No, as you said that, as you mentioned that if their PDFs factorize, then
Yeah,
they are independent, and also if covariance is zero, then it doesn't guarantee they are independent. That's the, but we can, yeah, we
yeah.
can
If
check.
you can write the PDFs to be,
Uh-huh.
yeah, if you can write the PDF to be product of simple PDFs, then they are actually independent. Yeah, the probably the easier way is that if you calculate, where did I show that? Variance matrix, no. Yeah, here, here, yes, right. So here, if you calculate, say, um, okay, but if you, yeah, if you calculate the mean, this one to be same as product of their mean, then this is, then this would be, then that would give you basically something, but
Yeah, I think
it's
one
not,
just has to see if you can
yeah,
factorize their joint
joint
PDF into
PDFs.
two. That's the
Yes,
only way we can see.
exactly. If you can factorize the PDF to be their joint PDF to be um, their individual PDFs, then yes.
Yeah, maybe I when I do the exercise, I can try to tell at that point. Maybe I can see if in the exercise I can mention.
Okay. Okay. So okay. So this is the definition of the Jacobian. I guess you will hear more and during the tutorial. Now, okay. Now let me go to the error propagation. So this is something that all of you have to do. I mean, to do in practice. Okay, whenever you do some calculations of any results of some experiments. So why do we do error propagation? As I said, if you have, say, a function of x, a function of some random variables, if you know the PDF, the whole PDF of x, then you can calculate the PDF of y, and then you calculate their mean and see errors. But in most of the cases, when we get the result of from some experiment or some calculation, so we get errors, but we do not know exactly their PDFs, how the variable itself is distributed, right? So what we get errors, when we say errors, it's mostly what we say error is, in general, it's actually the standard deviation of their distribution, right? So that means when we get some number, say like a plus minus delta a, that we basically getting their mean and the corresponding variance or the standard deviation. So given that, if we have a function of y of that uh, of x, then what is the mean and variance of y? Okay, how do we approximate that? So that approximation is called error propagation. Okay, so what we can do in this case, when we do not have the PDF, then what we do is, let's um, when we have y as a function of x, let's expand this y um, in around the mean value, so we can uh, do this expansion. So then y of x can be written as y of at mu plus um, del y by del xi at x equal to mu times xi minus mu I plus additional terms. Okay, so now let's if we neglect the higher order terms and keep only up to the first order, then we will get this result. Then from here we can see that if we take now the expectation value of y of xi, then from this equation you can see that this will be expectation value of this plus the expectation value of this. Now you know that the expectation value of this would be 0 because expectation value of xi is equal to mu I, so this will cancel out. Okay, and so you will get that the expectation value of y is simply the expectation value of y of mu. uh, Sorry, it's basically the y of the expectation values mu. Okay, that means the um, the values y or the mean y is simply the functions of the corresponding mean values. Okay, so this, that's why if we say y equal to say x plus or z equal to x plus y, okay, and we are taking x and y values that are basically their corresponding mean values, okay, then we simply take the sum, and then the corresponding variance, which you can write like is this. Then if we then again expand this y square term, okay, around its mean values mu, then you can again write say y square to be y square. So I think this should have the expectation here. Okay, plus these terms. Okay, so in this case you can see that again the second term here will vanish, this one, so we'll keep the third term here. So the third term in this case will basically give this partial derivatives times the covariance or variance of the xi's. Okay, so then you can write the sigma y square here. So sigma y square, then if you put this into here, that will give you sigma y square. So then that will be basically, so in that case this term would be same as this term, and so what will end up is this. Okay, now if you have x and i's are simply uncorrelated, then in that case Vij will be simply say diagonal, so sigma I squares. So in that case you can simply write sigma y square is equal to square of this partial derivative times Vij. Okay, in this case these are sigma I squares. Now if you take a special case, say y equal to x1 plus x2, assuming that x1 and x2 are the mean values of the corresponding distributions, okay, then what you will get from this equation is nothing but sigma y square is sigma 1 square plus sigma 2 square plus twice of v12. Okay, and similarly if you take the product, you get sigma y square by y square is sigma 1 square by x1 square plus sigma 2 square by x2 square plus this term. So this is the kind of thing that you have been using probably already when you do small experiments and you do the error propagation, right?
There is a question.
Mm, Sorry, I have a fit of double-sided crystal ball functional data. The mu and sigma of the fit have some errors. Yes, how do we find the error in sigma over mu? Yeah, so that is the relay sigma. Yes, so you
We'll
can use
research.
this. You can use this function here. Okay, um, to calculate this.
Yeah, we'll do one such exercise where you'll be calculating uncertainty on. factor like sigma by mu.
Okay, great. So here, if you that's what some exercises I give. So you can recalculate this from here. You can recalculate, all these things for this kind of functions, and what you get for this one, that is the one that you are going to use. Okay. Okay. Uh, Now you can consider a general case. So general m functions of x, that is, suppose y is a m dimensional vector of x i's. So then for all the i's, you can have, again, the um, covariance matrices for the y's. So that you can say, right, say u of kl is covariance of yk times yl. So that will be again, sum over this partial derivatives times the covariance matrix of the xi's. So in matrix notation, you can write this, that u is simply a b a transpose, where a matrix is basically this partial derivatives. Okay. And if xi's are uncorrelated, then this will become diagonal, basically sigma I square, and so you will have UKL is basically this partial derivatives times this sigma I square. Again, this will make it also diagonal. Okay. Now we know how we can propagate the error, and how we can use that to calculate the corresponding, how we can calculate the partial derivatives and the Jacobians. So now, suppose you have a set of variables or distribution which where the variables are correlated. That the example that we saw, the correlated Gaussian distributions. Now, if you want to say do some transformations which will make them uncorrelated. For example, in some cases you might need this kind of things. Maybe in some machine learning algorithms, like there is going to be an exercise probably. So if you need to uncorrelate them, some of the algorithms which may not be able to take into account the correlations between different variables, in that case it's better to use uncorrelated variables to extract maximum information. So if you want to do that, then in that case you can uh, do a transformation using simply a linear transformation of the variables. Say if I have xi's or xj's are my random variables which are correlated, then I want to get a variable set of variables yi's which are uncorrelated. I will do a linear transformation using some matrix aij. Okay. The question is, how do we construct such matrix? Okay. Now, when you write this covariance matrix for y's, so uij, so then that makes the covariance of this, so which is nothing but the sum over ai's times the covariance of xi's. Okay. And that you can see if you write this in terms of matrix elements, so it will be like aik pkl then alj transpose. So a is the matrix a, and b is the matrix covariance matrix of x. Okay. Now this is basically the simply that special case of the error propagation formula that we saw here. Okay. Now the idea is that for uij to be, say, um, on diagonal, so we have to find a matrix aij which makes this diagonal. Okay. So we should have matrix A. So this is when you do this transformation, then it makes U diagonal. So this is very this kind of problem you have. I mean, in linear algebra. So basically, this is a diagonalization of real and symmetric matrix. So what you can do is find the eigenvalues and the corresponding eigenvectors of V. Okay, then once you have the eigenvalues and then the eigenvectors, so the eigenvalues lambda is will be the diagonal elements of U, and then the matrix A can be constructed from the corresponding eigenvectors of V. Okay, so that is Aij will be Rij, and Aij transpose will be Rji, and then you can also show that when you use that, then you can recalculate Uij. It will you will get that would be equal to lambda j delta ij. Okay, um, and since the eigenvectors are orthonormal, then this matrix, you can also see that the transpose of the matrix is its inverse, and so this transformation is an orthogonal transformation, and this basically corresponds to say a rotation in of the vector space x into some y, such that the uh, you know and the xy square is same as y square, the magnitude remains same. Okay, now you can take a special case or example in 2D. Say suppose we have two variables x1 and x2, and this, then the covariance matrix can be written in terms of their individual standard deviations. Say sigma 1 square, the diagonal term are individual variances, and the off diagonal terms can be written in terms of rho. So rho times sigma 1 sigma 2. Okay, then if you take a solve this eigenvalue problem for this matrix, then the eigenvalues will be like this. Okay, and then you can define their orthonormal eigenvectors in terms of some angle theta. Okay, so then you can write say r is cos theta, r plus is cos theta sin theta, and r minus minus sin theta cos theta. So that's basically rotation, as we said, and substituting back into this eigenvectors to this eigenvalue problem, so it will give you the theta is tan inverse this quantity. Okay, and then you can write, you have this the desired transformation matrix A, so given the correlation that you want, okay, sorry, given the correlation from your distribution of x1 and x2. Okay, so you can construct the matrix, then you can diagonalize it, and then you will find the corresponding theta values, and then you will have the transformation matrix A, and using that transformation matrix, if you have, you can transform them or rotate them to make them uncorrelated. So the suppose this yi's here are a correlated variables. Um, in this case, then this is being rotated or transformed to a set of uncorrelated variables x1 and x2, which is this one. Okay. Yeah. So you can use this also in the exercise to do some. I think there are some exercises for this. So this kind of things will be useful, as I said, in some of the ML algorithms, like say maybe decision trees. I do not know, maybe in support vector machines, random forest, these kind of things, which where you cannot basically, which do not take into account the correlations of the variables very well. I think that's it from my side. I finished in time, I guess. If you have any questions, maybe you can discuss before going to the tutorial. Can you hear me? Hopefully, yes.
Yes, 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 we can hear you. So someone is saying, okay, could you please share these updated slides before exercise?
Okay, I think yesterday I shared, let me.
Okay. So, are we done for today's lecture?
My lecture is over.
Okay.
This was my last
Certainly.
slide.
So you can. So about 5 minutes break. I would say a lot of you are here. I think you can have a break right after the quiz because it's very difficult to make sure that everybody is back. Okay.
Yeah, and please don't leave
So,
after the quiz. We'll have tutorial.
yeah,
I'm saying
Um,
don't
yeah,
leave
what?
after the quiz.
Yeah, yeah, and don't leave after the quiz. Yeah, so let me just activate the quiz.
yeah, okay, Opera, there's some questions.
Hello, sir. So I have a basic doubt. So earlier in the previous slide, you were talking about the correlations, and yeah, here only this. So I'm not getting this idea. Like, if we are saying how much correlated are these, so do we have any confidence interval, and how do we get it? Like, how we make sure how much correlated it is, like that.
So you are saying how do you get how much correlated this is, this
Yes, sir.
variable?
Yes, sir.
So this is how you will calculate here. So you will calculate the covariance uh, uh, matrix of from these distributions. So the covariance matrix, as I said, is a what did I get? From the distribution, you can always
So,
calculate the covariance matrix. Let me go
so
back
sir,
to the
I
definition
guess
of
in
the covariance
Python,
matrix.
so Jacobian, are you talking about Jacobian thing?
No, no. I mean, it is just a simple XY I mean, X1, X2 variable. So you will, from this distribution, you will calculate its corresponding covariance matrix, right? So to know what is their, you know, standard deviations and the correlations.
So,
So
sir,
from
in
there,
this,
so you can do, you can calculate the covariance matrix, which is defined like this, right? So you can say, even you have a discrete points, so this will be basically, the integration will be basically replaced by the sum, right? So you will basically take the sum of xy's minus, or yeah,
so
average
sir,
total mean of
is
x y minus individual means. So that will give you the covariance matrix, and then you will also calculate their individual um, um, variances, and then from there you can calculate the row.
yeah, sir. So basic idea I got, but I'm asking about the Python. Like in Python, when we are doing the coding, can we get this correlation number directly, like without solving on our own?
Oh, that there is a in NumPy there is a method called covariance. You can use that.
Okay,
Given a
okay,
data set, you can always use that function to get the covariance matrix.
okay.
Yes,
Thank
but
you,
in
sir.
the exercise that I have, I would ask, I would prefer all of you to do it by hand
Yeah.
because it's like a
So
more
this is a very simple.
learning exercise.
This is a few lines of code that you want to do.
Yeah.
It's a basically four averages. Oh, sorry, three averages that you want to calculate, right? From here, three or four averages that you want to calculate to get this. So the covariance mat will be this one, and then individual mean and individual variances. So from there you can calculate this, and that would not take very difficult. If you have a set of data, you just loop over them, calculate the individual ones. I mean, using some function from Python is okay, but you want to learn it how it is being calculated.
Thank you, sir.
Okay. So now I'm gonna put the quiz thing on the chat box.
I
Yeah. You
stop
can stop
sharing.
sharing the screen, maybe.
Yeah, okay.
Here is the quiz. So your timer starts now, and this will be for 5 minutes. I'll announce 30 seconds before stopping it. So in 30 seconds, it will be over. Okay, so I'm stopping it. Time is up. Yeah.
Ritesh, do you
Guys,
release this course also? Yesterday, I think we didn't release anything.
okay,
This
so I'll
course.
release I'll release all of them
Okay.
one by whatever is done. Yeah. So quiz is done, and now we can take 5 minutes break, and we'll be back for the tutorials by Shilpi. And in the tutorial, as Shilpi said, you should write your own snippets of code in Python to compute all the correlations and means and all that. Shilpi, do you also ask them to share the screen or something like that?
No, yesterday I did not ask. Today I can actually do that.
Yeah. So that way you can choose the name and say this person should share the screen and show the.
Okay. Okay.
Yeah. And if somebody a volunteer, of course, we ask them, of course.
Okay.
Okay. We certainly respect the volunteers, but otherwise also we can ask that you can share the screen. If the person is hesitant, can say that I'm not.
Your voice is breaking.
Internet is really pathetic.
Okay.
I'm working from home today.
But I could understand what, I mean, make out the meaning of it, what you're saying.
Yeah.
Yes, that's right. Uh, that's how the covariance, the sigma square y will be.
Yeah, I guess we have 5 minutes over.
Okay, so I start. I start.
It's 11:30 now. Yeah, yeah, I guess you can start.
Okay, okay. So
Yes,
first
yes,
of
yes.
all, there are two things that I would like to mention. I would like to acknowledge the help I've got in the coding. So yesterday's code for exercise number 4, that was on Bayes theorem, how to in the coin toss, how to feed the knowledge gained from the previous experiment to the next experiment. That code was written by a starting PhD student from SINP. I think he's connected, Laltu Ghazi. He wrote it last year for last year's school in IOP. Then for today's exercise number 4, I've taken Arun's code. So thanks, Arun. And then um, because I was running out of time, I've taken extensive help from ChatGPT, so I should acknowledge that as well in writing my codes. Okay, so yesterday I shared a feedback form for yesterday's tutorials, and I see that many people want me to repeat all the 4 exercises. So I think it's a good idea if I can repeat, just to make sure that everyone is following. However, I think I won't repeat it right now. I'll start with what we did today, and then if there is any remaining time, I'll do those exercises. Otherwise, I'll take those exercises up either on Monday or Tuesday, whatever problem. So I'll again share the feedback form today, and then I think last day on Tuesday we'll see if I can if there is extra time for doing all the remaining exercises, or I can take sort of an
I
extra
think,
class.
Shilpi, I think what we can do
Uh-huh.
is on the last day, Tuesday, we can keep it for this, that all the exercises that
Uh-huh.
they want to repeat, that we can do that day.
Uh-huh.
And
Okay.
the whole day we can maybe devote for the exercises. Probably
Yeah,
there
yeah.
will be lecture on that day.
Yeah, yeah. Okay. Okay. I think that's a good idea. Depending on how what feedback I get, so I'll again share today. If everyone wants a repetition of all the exercises, then we'll see. Okay. So let me share the Google Doc of my exercises for today. So I'm not going to share the Google Doc here. I think if everyone can open the Google Doc on their screen, that will be much better. Instead, I would like to do the explanation on my tab. So I think everyone can see this.
Yes, yes, we can.
Okay. So let's understand what the first exercise is about. So in the first exercise, um, what we are asking, just a second, I just need to minimize the screen. Okay. So the first exercise, I'll read to you first. A random right triangle can be constructed in the following manner. Let x be a random angle whose distribution is uniform on minus pi by 2 to pi by 2. For each x, construct a triangle as pictured below. Here, y is equal to the height of the random triangle. For a fixed constant d, meaning the base d, find the distribution of y. Okay, so you have a coordinate system. Then what you are doing is you have a fixed base d. This is fixed, you know. Now you, oof, okay. Now you are throwing angle randomly like this, right? Uniformly. It's all uniform distributed, meaning the probability of getting angles near 0 is the same as probability of getting angles near, let's say, pi by 2. So you are doing it from minus pi by 2 to pi by 2. Okay. So Now the question is, what will this length follow? So this is going to be random, you see. So again drawing, you threw a random number theta, you got this y. You again threw a random number theta, let's say theta 2, you got this length y2. So you have to see what is the distribution of these y's. Is it going to be uniform? How is it going to be? Any guesses? You got the question? Sorry, I cannot hear. You're saying it will follow tan theta? Not really, but this will come in calculating the PDF. But everyone got the idea of the problem?
Yes, ma'am.
Okay. So how will you go about it? Remember Jacobian? We did this exercise. So um, so essentially here you're going, you know the distribution of x or theta. In the question I've written x and here I have written theta. So you know the distribution of theta, right? It's a uniform random variable, ux or u theta. Okay. Now you know how theta and y are related. Y is equal to d tan theta, right? Or y is equal to d tan x, if you call it x. So you know the distribution of x, PDF of x, it is uniform, meaning from minus pi by 2 to pi by 2, the distribution of x is uniform. In order to look at the distribution of phi, we learned that we always use Jacobian, right? So how? Arun had a very nice picture. So let's say there is a relation between uh, x and y. Then let me actually just open his slides also. If you have got the link to Arun's slide, then go on slide number, I think it's 44, no. Or I'm using the old slides. Just a second.
It should be 53, I think. The point.
53.
No, the
No,
new.
no, 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 no. It's 52. It's 50, 52, 48. 48. Yes. So you can go to slide number 48 and you can see. So if you have two variables related, then g of phi is equal to mod of dx by dy f of x, where f is the PDF of x, this is called the Jacobian, and this will give you the PDF of y. So can you now calculate this? So I'll now wait for you to calculate, and if someone can volunteer to share the screen or wherever you are calculating, just give me the answer what you get. Is the question clear to all? Can people say yes or no?
Yes, it's clear.
Yes.
Okay. and make sure that your fx is not normalized. Let's say fx is a uniform distribution, meaning let's say it's constant k. So also normalize to 1 this uniform distribution uh, from between minus pi by 2 to pi by 2, and calculate the value of that normalization constant. But that can be done later also, so that's not a problem. Just telling that a uniform distribution is represented by k. You just have to evaluate the value of k by doing this. Has everyone got the answer same as Deep Jyoti, or is it different? It will be good if you can keep raising your hands if you have done the exercise, so that we can I mean I can tell you something about it. So I see only 13 hand raises out of 68. You can type your questions if something is not clear. I'm hoping to see more hand raises. Okay, you lost connection after I said Vaikulu 10x. Okay. Um, so you want me to explain this part again, I guess. So what I was saying is that y is um, related to theta or x. I mean, I am using these two variables interchangeably, theta and x. Y is equal to t d tan theta. So you know how the theta is distributed. Theta is uniformly distributed between minus pi by 2 to pi by 2 because that is given in your exercise. Now, if you know the distribution of theta, can you get the distribution of y? So, meaning I know that theta looks like this uniform distribution. Is y going to look like this, or is it going to be uniform or something else? So for that, we learned something today in the and you can go to slide number what was the slide number? Slide number 48 of today's lecture. You see the usage of Jacobian. So we had this very important expression for transformation in one dimension. So PDF of y is given as, if x and y are related, PDF of y is given as, meaning g of y is equal to dx by dy into f of x. F of x is the PDF of x. Dx by dy is called Jacobian. I'll tell you I'll later on tell you what this Jacobian does, and then intuitively, I mean, and then g of y. That's how you get g of y. Is that clear now? So now you know what is f of x. You can calculate dx by dy to get g of y. Is that clear, Aradhna? Okay. I
There are
think I
several people they have raised their hands, I think.
okay. I think I can. If the question is, but why is not everyone raising? I'm just thinking. Okay, fine. It's not even 50% who have raised their hands.
Only
So I
20,
can, huh?
22 people.
Okay, fine. So I can assume that everyone understood. Otherwise, I'll again send a feedback form so you can fill that in. So now let me move ahead. So exactly what you will get is what is being written in the chat also. You will get it to be d by d square plus y square. Okay, into 1 by pi. Now, if you look at today's slides, we learned about Cauchy distribution. So this follows exactly like Cauchy's distribution. And Cauchy's distribution usually you come across when you look at the decays of a resonance particle. For example, if you look at the distribution, if z decays to e plus e minus, if you look at the invariant mass of e plus e minus, it follows Cauchy's distribution. It's different when you have detector effects in. It doesn't look exactly like Cauchy distribution, but yes, at very before the detector effects come in, it looks like Cauchy distribution. So now, can anyone tell me theta theta was uniformly distributed, but why is y decaying or is spreading out in the tails, meaning here sorry, it's spreading out in the tails, meaning for you see for large angles it's becoming more and more sparse. Can you just think why it might be happening?
It's because that
Anyone?
while yeah, it's because while x is going to its extremum, like minus pi by 2 to pi by 2, then the y
Uh-huh.
value goes to infinite, but like uh,
Yeah.
so that spread is because of that only.
Yeah, exactly. So when you are very closely spaced, then when the angles are very small, then these values are also meaning sort of closely spaced. But as you are increasing the angle, Even a small change in the angle will give you a large change in the y-intercept, which means here I got, let's say, this angle. Okay, I cannot go beyond now. If I make a small change in theta, it just gives me a huge change in y, which means the values become very sparsely spaced. They become very sparse at large angle. So that's the, which means the essentially the work of the Jacobian is to compress or stretch the distribution. So to me, it's very interesting that to start with you have a uniform distribution, but by just changing it, you can get a very non-uniform. You can like stretch it from some sides and compress it from the other sides. So uh, that's the first part of the exercise. Um, Now going to the next part, can you write a code where you generate uniform distribution of x? So this you just did analytically. Calculate y and then put that value of y in a histogram. And then see, just confirm for yourself that it indeed looks like a Cauchy's distribution. And how will you confirm? Once you have done the histogramming of this y variable, just fit it with a Cauchy distribution. And I'm going to share the codes for today, which I completely forgot. Copy. Here is the here are the set of codes. And the code named line segment, uh, sorry, just a second, line segment making angle underscore Cauchy. So I think it's a good idea if you can just do this. So first, throw uniformly generated random variable x, that will be your theta. Then estimate y and just put that in histogram for something, let's say 10,000 times, and then fit it with a Cauchy distribution. That way you will be convinced that indeed it's a Cauchy distribution. So you see, you are learning two ways here. You are first analytical way, and the other one is sampling or doing a Monte Carlo experiment. Everyone got the idea? Yes, no? Okay, thanks. Could you repeat the example of Cauchy distribution that you mentioned? You
Shilpi,
mean yes.
there are about 11 people who have raised their hand.
Oh, they
In
have
the
questions.
Yeah, they have their hands are raised. Okay, some
Okay.
of them are lowering. So Dinesh Jaswal, uh, okay, he removed his hand. Maybe he answer his question is
Actually,
already
that was
answered.
Okay.
raised when ma'am asked for that if the question is
Yeah,
solved.
yeah.
Then
Okay. Okay. So someone has
Then
asked, could you repeat the example of Cauchy distribution that you mentioned? You mean which part of the example? Can you please tell from the beginning or from the second part of the exercise or the stretching?
can you repeat
Atul,
your question, please?
Atul, can you please repeat what would you like me to repeat in the example of Cauchy distribution? Is it the stretching part or the next exercise of Monte Carlo uh, throwing several events? Okay, I'm not sure if. Oh, the detector effects.
Uh,
I missed the point. Okay, okay. Sorry, I
yeah,
didn't scroll down. So what I meant is, if
Saswat
you just
Gaur, sorry, Saswat
raised a hand. Okay, I'll. Yeah, yeah. I saw the raised hand. I'll
Gaur
take the.
also has a question.
Yes, yes. I'll take the question. I'll just answer about the detector effect. So what I just meant is, if you just catch, so somehow if you just look at the distribution, so z decays to e plus e minus. I was just giving that example that z decays to e plus e minus. And if you just look at the invariant mass distribution of these two electrons, just at the notebook level, or the Monte Carlo or the generator level, as we say, then you will see a perfect Cauchy distribution. But because that you need a detector to observe electrons and everything to measure their energy, what happens is that um, their energy gets smeared out because of detector resolution, meaning if it was 50 GB, in actually at the truth level it's not 50. You might be reading off as 52, you might be reading off as 48. So so then when you form the invariant mass, it has an effect on the invariant mass, right? So it doesn't remain exactly right Wigner, it gets convoluted with Gaussian. So that's what I was saying, just some additional information, but not important for this exercise. Okay, Shashut doesn't have a question. So, has everyone done the exercise? So you could generate 10,000 events and check for yourself that it is indeed Cauchy, right? So I think if you have got the idea, I take that most of you have understood the concept. If you haven't been able to finish, I would say that go back home and then do it. I'll move to the next exercise because I have only half an hour left now. If anyone has any urgent question from the exercise, then you can ask now and I can take it. Otherwise, I'll move forward. Yes, is there a question? I'm unable to get you, Shashit, because you're cutting. I mean, your voice is not clear. Can you please type, or can you try speaking again? Yeah, yeah. Can you try speaking a little louder, please? Maybe you can type because I am unable to understand. We will generate the X values using uniform. Yeah, yeah, using uniform distribution first. Indeed. Then could you please share the last few links again? Okay. Exactly. Then feed y equal to d tan theta. Indeed, that's how you will go. And then for every value of y that you get, just put it in a histogram. Then again, generate x, calculate y, put it in a histogram. Exactly. And then fit that histogram with a Cauchy distribution. Just a second, the last few links were lost and I'll share again. I'm pinning them. Okay. Let's move to the next exercise now. So, um, if there is a random variable x, and this has a PDF of x minus 1 by 2 for one between 1 and 3 and 0 otherwise, find a monotone function ux such that the random variable y has a uniform distribution, uh, has a uniform distribution between 0 and 1. Okay. So what this means is, if I have an a random variable x, and its PDF looks like this. So this is x 1, sorry, 1 3. Its PDF is like a triangular PDF. What this means is that if you sample x out of this PDF, you will most of the times get values near 3. Very less often you will get values near 1, and beyond that you will get nothing. Okay. So now the question is that what is the relation between y and x, meaning you have to calculate this if y is a uniform distribution between 0 and 1. So this I think you should be able to calculate now. I will not even give a hint. I'll give it later. So, but I guess everyone got the question right. Okay. Any questions on this explanation? Okay. So, does anyone want me to repeat it again? Okay, I will repeat it. So, the question is, let me again switch there. Okay. The question is, there is a random variable x. Its PDF is given by fx equal to x minus 1 by 2, which means, and beyond that it's 0. So if I plot the PDF of x, meaning on the y axis I have fx, on the x axis I have x. So the PDF is non-zero only between 1 and 3. Beyond that it's 0. So that we know. Now you plug in the value of x equal to 1. Here PDF is 0. But you see it's linearly rising, right? If you put x equal to 2, then it becomes 0.5. This thing becomes 0.5. You put x equal to 3, this thing becomes 1. Okay. So which, this is a triangular PDF, which means if you sample the value of x from this PDF, most of the times you will get values near 3, because here the PDF is higher, right? It's the highest here. And then it keeps on decreasing, which means the probability of finding x with values less than 3 keeps on decreasing. So very less often you will get values near here. So the question is, for what relation between y and x, meaning y of x, will the uh, PDF of y, meaning g of y, will be uniform between 0 and 1? So again, it's like, it's you can think that it's sort of related to, if you know the PDF of one, find the PDF of other. Here you know the PDF of both, find the relation between the two. So you can again use the technique of Jacobian, which is g of y is equal to dx by dy f of x. So you know this, you have to calculate this. Yes, you will have to integrate. So you got it, Nana and Deepak?
Yes, ma'am.
Okay. I think it's an easy one, but I just want, after this, once we have done this, I just want to demonstrate one thing. Yes, it has a unique solution. Can someone tell me the answer? No, it's, yeah, the last one is right. Okay, I think if you don't have any other questions on this, then I will move ahead. Last call for questions. No one, then I'll move ahead. Uh, they are equivalent solution for C equal to 1. What is C here? Sorry, I missed it. The constant of integration. Okay, okay. Okay, so I just quickly want to do tell what is happening again here. So you might so what do you see, that you have this kind of PDF which is very much sharp peaked here and very sparse here, but out of it you are able to get a uniform distribution. So again what is happening, so let me just give you an example. So for every x, let me calculate the value of y from the relation that you have got, x minus 1 square by 4. So when x is equal to 1, then y is 0. When x is 1.5, y is 0.0625. When x is 2, y is 0.25. 2.5, y is 0.5625. Then when it is 3, y is 1. So you can see that for a change of by 0.5, you are sort of just for a change of uh, zero point 0.5 here, from 1 to 1.5, you're just changing by the values of phi between 0 and 0.625. Whereas for change with the change of 1 unit in x, you're changing, you are covering a bigger range. I mean, this is the region where x is getting values most of the times. and those values you are able to cover a large range, which means you're sort of stretching out this region, the high X region, and you're sort of compressing the low X region. So so you can imagine that you are uh, in this range where the data is very sparse, you're compressing it into a small range so that you get many more events here. Uh, but in this large range, where you get many more events, you are actually covering a larger, even larger range. So that's why it's becoming uniform. I just wanted to tell you why Jacobian is. I mean, the function of Jacobian is again compressing or stretching out the distributions. So there is a question: why are we taking C equal to 1? That I have to check in my solutions. Just a second. Uh, so here we are actually not even talking about the constant of integration. We are not doing the limits of the integration at the moment. So the final answer is uh, G of phi is equal to uniform distribution, and uniform distribution is between 0 and 1. So you always represent a uniform distribution by K, which means between, you just normalize to get the value. So you always normalize this to get the value of K. This area has to be equal to 1, which means K is equal to 1. Essentially, Gy is equal to 1. And you know what f of x is? F of x is x minus 1 by 2. Just a second. Yeah. So then you just plug this in. And just integrate. Okay. Okay. Is that fine? Yes, I think you can. Yeah, I think you can do that, and that way you can find the value of C. Indeed, I haven't checked that, but all of you should check that. If we take y3 is equal to 1 or y1 is equal to 0, then you can calculate that. Okay. Okay. So I'll now move to exercise number 3. This will help you understand how error propagation happens. So before I start with the exercise, let me remind you that the formula for error propagation that you saw is sigma y square. Sorry. Let's say um, y depends on certain variables. Okay. Then in today's slides, you saw this thing. right? If let's say just y is just a function of x, let's say just one variable x, then sigma y square becomes just del y by del x square into v11, where v11 is just the sigma x square. So essentially you can also see y, so sigma y is equal to del y by del x sigma x. I just want to show you just geometrically. You can see one thing here, that if x is just giving you the reason why it is like this. So let's say there is a function like this, and your estimate of x is this, and your error on x is this, let's say. Okay, so your estimate of y is this and your error on y is this, right? But now if you make the slope a bit steeper, so you can see for the same change in x, for the same error in x, you will get a lot more error in y, right? Depending on how the slope is. So that's why sigma y is proportional to this dy by dx. I just wanted to show you this thing once. Um, uh, um, Everyone got this idea? Okay, okay. So uh, now, now let's move to exercise number 3, and keep in mind this equation. Okay, let me also tell you what Vij is. So Vij is the covariance matrix. Let's say y is a function of two variables. Then using this expression again, okay, now it's two variables. So just sum, meaning take ij from 1 to 2. So you will get dy by dx1 square v11 plus dy by dx2 v22 plus dy by dx1 dy by dx2 v12 plus dy by dx2 dy by dx1 v21. v21, it's v12 is the same as v21 because the way it is defined. So let me define what is v11. v11 is just the variance of x, which is x minus xi minus x bar whole square sum over I 1 by n. So this is variable 1 I. Okay, v22 is just the variance of the second variable. Okay, and v12 is xi1 minus x1 x2 I minus x2 bar. Okay, that's it. And then this term becomes like twice of dy by dx1 dy by dx2. So let me again write this. Error on y, or variance on y, will become del y by del x1 square. If I call this as sigma 1 square plus I call this as sigma 2 square, and I call this as sigma 1 2, del y by del x2 square times sigma 2 square plus 2 times of del y by del x1 del y by del x2 sigma 1 2. Okay, so that's the formula. So let's say if two variables are not correlated, this would mean that this is 0, then this term won't appear. Okay, and here from here you can see that two independent sources of errors are added in quadrature as well. In quadrature meaning just take their square and sum them up. Okay, so now if this is clear, then we can move on to exercise number 3. 3a, a student measures the energies of two particles in a collision. E1 is this, E2 is this. Find the uncertainty on E1 by E2. So there was a question in the class today. I guess this will be useful if you can estimate. So whenever these questions are there, just estimating the uncertainty, just use linear propagation of error, meaning the expression that we learned today, meaning this one for two variables. But then you can extend it to 3 variables or more than 3 variables by using the generalized form. Remember, this is also an approximation. So can you just tell me the answer? Is everyone with me, or have I left people behind?
But this is surprising that now we have some 60 people.
Sorry?
I thought we had more people earlier. Now we have 65.
No, they okay. I thought they were, yeah, I think after the quiz people left. I've been seeing it's around 65, 66 only. So can you tell me the answer? Uncertainty on the ratio of E1 by E2. I mean, you can tell me the value, Deepjyoti. But your expression, I think, looks fine to me. Maybe there is something missing in the denominator, or it's already there. You can check, you can just tell me the number that you're getting. Yeah, I think everyone will get the answer. 0.18 or 0.179. That's the answer. Okay, so I think if are there any questions on this part? Don't hesitate to ask. Then I'll move to the next exercise. Now, the B part is this. I think this will give you some idea about what are systematic uncertainties and how do we deal with it. So now let's say that E1 is 50 plus minus 1.5 MeV and E2 is 70 plus minus 20 MeV. They share a systematic of 1 MeV. What's the uncertainty on the sum? So can anyone tell me, is uh, is there a source of some correlation between the two or no? In the first question, I said, I think I mentioned explicitly there is no source of correlation. But in this, do you see a source of correlation between the two?
Since it is given the systematic of one, so might be there is a correlation.
Yeah, exactly, exactly. So systematic effects, they tend to. So let's say if I am measuring E1 and E2, if they the due to systematics, E1 the value of E1 increases, then the value of E2 will also tend to increase. So they sort of have a correlated effect. So the other uncertainties in the question are, they are statistical uncertainties, and statistical uncertainties are always independent. Are yeah, in our cases they are always independent, so they don't cause correlations. It's the systematic effects that cause correlation. So now, how will you go about it? Remember that that in the exercise, in plus minus, what is given is just the systematic effect. So for each variable, remember that its sigma 1 square uh, is square root of sum of both the effects. Okay, that will be the sigma 1, total sigma 1. So can you try solving this part? First, you have to estimate all the elements of the covariance matrix, meaning sigma 1 square, sigma 1 2, sigma 1 2, and sigma 2 square. I have given you an idea of what sigma 1 is. Follow the similar idea on sigma 2. Then I also said what causes these elements are essentially what bring in the correlation. So just think what is bringing in the correlation. Uh, so that will tell you what is sigma 1 2. Has everyone got the question? Oh, can you please explain why systematic effect? So systematic, okay. Okay. So let me take an example, a simple example of a scale. Let's say your scale is miscalibrated, and instead of you did not know, instead of the actual 1 mm, it was giving you somehow 1.5 mm. So every length that you measure, that will have that systematic effect, right? It will be measured, uh, it will be measured off by that effect, not just one. Whatever length you are measuring with that particular scale, every object will have that systematic effect, no? So which means if length of object 1 is has that uncertainty, has that systematic, length of object 2 will also have that uncertainty. So if it tends to if the scale tends to measure it higher for object 1, it will definitely tend to measure it higher for object 2, which means you see there is a correlation. Do you see now? Do you want a different explanation? Okay. So so let me again, I think some people want me to explain this problem. Um, so let me just go to the exercise again. E1 is 50 plus minus 1.5 MeV. E2 is 70 plus minus 2 MeV. And then they say that the systematic effect is 1 MeV. So this is, they haven't explicitly mentioned, but because they are separately mentioning, just imagine that this is the statistics. So, you know, yesterday we read about the errors, statistical and systematic. So this is the statistical part. Statistics never causes correlation because um, this is because of the number of events essentially. Statistical fluctuate or the source of uncertainty due to statistics is due to the number of events. So they don't cause correlation. So this is the statistics part. But that's not the total uncertainty on this measurement of 50. They say that there is a systematic effect also, which means when you calculate the uncertainty on this, it has to take into account this effect, statistical effect, and then it also has to take into account the systematic effect also, right? And the way and statistical and systematic, they are independent sources of uncertainty. Whenever we have independent sources of uncertainties, we always add them in quadrature, meaning that will give you the total uncertainty on that measurement, which means when I quote E1, I should have actually quoted like this. Square it and sum it with the square of this. That will be sigma 1 square. Okay. Same thing goes with E2. Right. Now, the idea is to calculate the error on this measurement, E1 plus E2. Whenever you have to calculate error on any measurement of more than one variable, or okay, one variable or more, then you always go to this, this, okay, this expression, okay, which I simplified for two variables as this one. If you got this part, then which means you need to know what is sigma 1 square, you need to know sigma 2 square, you need to know what is sigma 1 2, and these are just the elements of this covariance matrix. Yeah, you know what is sigma 1 square, I just mentioned. It's just this sigma start square plus sigma s square. You can do the same for this, and sigma 1 2 is, these are the elements which cause correlation, right? Because you can imagine like this. Why do they cause correlation? Let me show you. Two variables. If you do this multiplication, then there is a term xy only if these are non-zero. You can multiply and see. So, which means these are the sort of correlation or correlated effects. So here what you have to put in is the sigma that is causing the correlated effect, which means is the sigma cis. Okay. Uh, are people following me, or do I need to explain? Can more people confirm if they have any question at this point or not?
Ma'am, how do you put that sigma 1 2 is equal to sigma 6?
Okay, sigma 1 2 is so sigma 1 2 here, the term that comes in, that causes the correlation between the two variables. Okay, that's the
Yeah.
sig. Okay, and I said that it's the systematics that causes correlation. Okay, so statistical part never causes correlation between the two. It's the systematics part that causes the correlation. So that's why I'm saying we can put here sigma cis.
But we are not sure that that variance is exactly the same as systematic error.
Uh, but that no, that's what I mean. This is this this variance is, so it will be just square of this, no? Sigma cis is 1, so I should have written, sorry, like this. Sorry, I should have written this square. This is because this is the term that is causing the correlation between the two. Does everyone have the same confusion, or otherwise I can think of another way. Yes, it includes our experimental setup and procedures, exactly. I mean, if I am using a procedure which has some bias, inherent bias, and if I'm measuring two quantities, then that procedure is causing a systematic effect. So, hmm, can we do it independently and then add systematic error? We always have to remember that we use this equation. This equation is the correct one. Can you write can you write in equations what do you mean by adding independently then add systematics error? That won't be the right thing, no? Because then you are missing some terms. For example, dy by dx1, dy by dx2. You're probably saying just add sigma 1 square plus sigma 2 square plus sigma 1 2. No, no, we don't do that. But then this will not hold every time. So what I will say, it's now 12:40. I wanted to really, I had even a lot more questions. I think they will take even more time, and but those are very interesting ones that will help you clarify some of the doubts as well. What I will suggest you is, if you can do the exercise number 3 fully, and if you can share your solutions in the same thread, then I can take up 4 and 5 tomorrow. And yeah, 4 and 5 tomorrow. If we know the systematic error beforehand, as in this problem, can't we subtract it from the data and treat the new data as uncorrelated one? That's a good question. Um, so you are saying that can we how will you subtract it from the data? Like, so you got one data point, let's say x1, you got some measurement. You are saying you just subtracted sigma, let's say sigma 1 2, you're saying like this, but how do you know that it has to be subtracted or it has to be added? I just know the number, I don't know the sign. Okay, okay, so here we don't know the sign, and you, if you know the sign, then you know everything. I mean, if you know by how, if I exactly know how much I'm off, let's say if I know that, like in my example actually, which was not very correct, in the sense that I knew that I'm off by zero point 0.5 mm, I know that I'm always measuring higher length, then for sure I can always subtract it. But we never know the sign as well, no? Otherwise I would have subtracted it. Then after evaluating V, what to find finally? So after you have evaluated the elements of V, uh, which means which means once you have evaluated sigma 1 square, sigma 1 2 square, sigma 1 2 square, these elements, once you know, then you know these values, then you just plug it in this formula. You can write this down. It's not zero. This I was just giving you an example if these are two uncorrelated variables. Okay. So are there any questions? Or do you think that the last exercise was confusing and you still have questions? So, so I can suggest you one thing. I will again send you a feedback form, and then you can write what exact uh, confusion you have. Okay. Why is a systematic error added in quadrature to the diagonal terms? So systematic error is something which is, so what I meant is, it's not added to the diagonal terms. So these are the diagonal terms. Are you asking about this question, about this line, sigma stat square plus sigma s square? What I was saying, when you do any measurement, it has both the sources, statistical source and systematic source. So when you quote any error, you always have to do uh, sigma stat square plus sigma s square, because that gives you the total uncertainty in your measurement. So yeah, sorry, diagonal. So indeed, so sigma 1 is essentially the total uncertainty in the measurement, total uncertainty. And your total uncertainty in the measurement is sigma stat square plus sigma s square, square root. Is that clear? Okay. Uh, Deepjyoti, is it clear? Did you get it? Why these are added to the diagonal terms? Or do I explain again? Sigma 1 is always the total uncertainty on the measurement, and the total uncertainty is not just statistical term. It should always contain the systematics if there are any, and in this case there are. So when they quoted 1.5, it was just the stat term, not the systematic term. So that's why I'm adding the systematics also. And then you're saying that even if E1 and E2 are uncorrelated, no, they are correlated. That's why they have, because errors on E1 and E2 are correlated. Exactly. So E1 is a variable, E2 is another variable. Their errors are correlated. There is a common source of correlation, and that is this systematic, 1 MeV of systematic. Is that clear? Okay. Anyway, I think I wanted to move much ahead, but probably it's better that you understand this concept and then we move forward. So, if you can finish exercise number 3 and check for yourself and share the answers with me. We'll do fourth and fifth tomorrow, in addition to the other exercises for tomorrow. And then I'll share the feedback form and you can just tell where are you facing the problems and where do you have confusions. Is that all right? So I think I'm done for today because it's already 12:46 and I
Okay,
have
thank you,
meeting.
Shilpi. Yeah.
Yeah.
So I guess I will stop the recording here.
One more thing, Ritesh, students were asking for the recording of the lectures. So
I will
please,
organize
please
it
share.
today and put it
Okay.
on, and I'll share the link. Yeah.
Okay. Okay. Thanks.